Hello everyone. Let's do some problems, some standard problems in static equilibrium. So you have to know what static equilibrium means to actually do these problems. So you might remember from your lectures, something like that, or you can go to my website to learn more about static equilibrium. And I'll just summarize just enough for us to do these problems. So static equilibrium is when every part, every particle in the body has zero acceleration. So it's neither, the body is neither accelerating, not deforming in shape, or changing, orienting in terms of angular acceleration in rotation. So in that case, suppose you have force F1 at say point P1, F2 at P2, so you got all these forces at different points in the body. That's at static equilibrium. Then clearly you have all the forces. So this is the sum of the forces. So suppose I have n forces. So the vector sum is 0. So if you have to break this up into x, y, z components, so this will be like a sum over fi x, sum over fi y, sum over fi z, independently will be 0. So potentially is going to lead to 3 equations. Okay. In most situations in current problem, you probably just have a planar forces. All right, so this is one equation. The other one is because it's got a net torque is also 0. So net torque by any force about any point O. So torque is actually is a vector. So this will have a orientation. So equals 0. Now, if there was just a so the axis, if the axis is z-axis, looking at forces in, so this will be the case if all forces are in say xy plane, then the rotation can only happen about the z-axis. Then this tau I will be like a clockwise, counterclockwise minus tau of all the i's in clockwise, that will be equal to 0. So clockwise, counterclockwise torques and clockwise torques, they should balance each other out. And this turns out to be very powerful, maybe most powerful for solving problems. And because I can actually choose, this pivot. Let me make it clear that this pivot can be arbitrary. So and why the pivot can be arbitrary is because all the forces, because the one pivot can be arbitrary. So these so about O and about some pivot. So because the pivot can be arbitrary, this is the most powerful of solving problems. So I can just keep picking pivot till I solve the problem. All right, so let's look at the problems now. So the problem number 1 is quite where should I place? So this is maybe find X, where to place this mass on a beam which is which has a support here. It's okay, so we will see that the beam is my system. So what are the forces on this beam? The center is over here. I mean, this one is not given. Let's call it this distance, it says A. So it's now let me look at, yeah. So weight of this big mg can be said to act on the center of mass or center of gravity as Earth is down. And then there's another force. You can see this weight of this guy is going to push on this, and there will be normal on this. So this, there will be mg will be pushing from the top onto the plank, and there will be a normal force here. So let's from this support, there will be a normal force from the support, and those are the three forces. And so we are going to try to do this first by picking a pivot. Here we know this and we know this, but we don't know that. Okay, maybe say you can know it by just by knowing by using one, but I don't want to use one. I want to show you that you don't need to use one, because I don't need to know one, so I need this because I can pick this as a pivot. So this is my choice of pivot. That's the most important part, that I can choose pivot. If I do pivot here, then this force is going through the pivot, so torque for this will be 0. About this O will be 0. That's why, so I don't need to know the normal force. That's the reason I'm picking the pivot there. Okay, so now you can see that this would be a clockwise, right? So this is clockwise, and this will be counterclockwise about this pivot. And so looking at this, over here is the normal force is that way, and this force is that way, and this force over here is that way. So from this is the lever arm for this guy, and this is the lever arm for that guy. So this distance is a minus x, and so this is L over 2. So so from here to here, so L over 2 minus x. So this distance is L over 2 minus x, because this from here to here is L over 2, and so, and this is A. So this is the lever arm for that, and this lever arm, this is the lever arm for that, and this is the lever arm for that. So we got A minus x times mg has to be equal to L over 2 minus x times mg times A. This is the equation, so that can be solved for x. They'll tell me g cancelled out, so I get a you can say m go over here, so m go over here. Then if I bring x on this side and a on the remain on the side, so x equals to a minus L over 2 minus a m over m. So that's the answer. Okay, so now you get an idea of how what are the many steps. We'll do all of these problems. Okay, So let me raise and get more clean place. Okay, so this problem here, it's called cantilever. Such a structure is this bar, when supported at two different supports like that, and it's hanging out this way. This thing is called cantilever. All right, so this is cantilever, and usually the question will be about maybe what's the force out here, maybe what's the force out here. So those will be the questions. Okay, so let me set it. Say I want to know what's the force that's going to be the bolt will be feeling, you know. So this is bolted in here, and there will be some force here. So I don't know what the force is. Okay, so let's look at the forces that we do know. So this is L over 2 and L over 2, and so this I'm using a small L here. So here, that's the capital mg. That's the weight is going to act the center. That's also something that you should use this fact and use the symmetry to figure out where to place the weight, because the weight is acting at all those places, and this is the symmetric point. Okay. All right. So there will be a force here. You can see that the bar will be pushing down, so there will be force there. So this is, say, F1, and then there is a force onto this pin, you know, that you can see this thing is trying to flip it like that, pushing in the pin. So pin will be pushing it down on, right? Pin will be pushing it down. Okay, I think that's all the forces. So I don't know F1, I don't know FP. Well, say what's FP gonna be equal to? Well, I just use this. I don't need to know F1, and I'm going to use this as O. So it's almost like that problem. So this is O, and FP is that way, and this is going to be lever arm for, because from here I draw 90 degrees, that's the lever arm. So this is A is the lever arm, and mg is that way, and then I've got this is L over 2, and so this would be L over 2 minus A. Okay, so now if this is correct, then let's look at this guy is trying to do clockwise, right? This is going to counterclockwise sense. This one is also clockwise sense. So this can't be one has you know, when I add them up, there's going to be not zero. So this using physical sense, I had come down correctly, right? So this is actually pointed down. It can't be pointed up, and then it becomes counterclockwise. So I had made a mistake over there, pointing up. And you can see originally when I made the argument that is when this thing trying to push up, the pin will try to push down. So that's where this down from the pin. Okay, now that you understand the direction, and so here it's going to be very similar. So I got FP times A has to be equal to mg times L over 2 minus A. And so FP is simply mg L over 2A minus 1. So that's the answer. And I will leave you with a problem that what's F1 then? So you can go out and use FP to figure out F1, or you can just set it up another problem in the torque. So what should be the pivot to find F1? So you can find that, okay? All right, so we got 2 of those problems down. Let's try to do the second, the third problem. I'll pause it. All right, so how about this problem? So this problem is, suppose you're pushing, so here is a log and here is a step, and you're pushing this log in this direction, which happens to be from the tip. If you go through the center on the other side, then this is 90 degrees. So that's the given. And so you want to be able to, so this support here. So you want to push with such a force so that you just go over the step, meaning you leave the ground. So find F just when about to leave ground. So it turns out that till you're resting on the ground a little bit, touching the ground or pushing on the ground, still the log is resting on the ground, there will be a normal from the ground. So there will be a force on normal, and this just means at time when n is 0. So I'm going to set it up so n is not 0, but then I'm going to solve it for n equal to 0. Okay. All right. So what are the forces? Well, there will be a force of gravity because mass m, so mg is that way, but that's the center, and this force is that way. And then there's going to be force, another normal from the tip of this, because I'm going to push against that, so it's going to be normal that way. And so this normal, let's call it n1, and so n1 is 0. Let's call this guy normal n2, and n2 we don't know. And the question is not asking for n2, so we maybe don't have to know n2. So it will make sense to put a pivot right there, right? So we just put the pivot over here. So that's the pivot choice. And we do it again this thing. So from here, this is 90 degrees. So lever arm for F, is 2 times the radius. This radius is r. Okay, and what's the lever arm for mg? Well, we have to draw a perpendicular to mg, so this distance will lever arm. For mg, you have over here, mg line is this way, and this distance is a, and this distance is r, and we want that distance. That is the lever arm. Well, how are we going to do it? So this is a here, so this is r minus a here, so we can use this. So the mg lever arm will be square root of r square minus r minus a square. See that? So this is right angle triangle. Okay, so I don't need to know n1 because I'll set n1 to 0. So you can simplify this guy. You have r square minus r square plus 2ra minus a square, and this is going to cancel out. And we are thinking of a less than r here. Okay, so this a less than r, the step is less than the radius. So with this, let's see which is clockwise or counterclockwise, right? So about this guy is clockwise, and mg is counterclockwise. So I have got f times 2r equals mg times square root of 2ra minus a square. So 2r goes down here, and so that's the answer for this. It's pretty easy, right? Once you get a hang of this, you just have to see where the pivot will be. We have set n1 equal to 0, so I didn't have to include that in the formula. All right, how about doing that problem? Okay, in this problem we have the bar, you might say a plank or something like that, and here is it's pivoted about that, and it rests on some maybe rubber stop. So it rests like this, and so here is the L over 2. So this distance is L over 2. So if I look at the forces on M, we're supposed to find the force that this will apply over here. So we don't know the directions of this force. So this is so what is the force by this? Okay, so let's redraw it. I didn't draw it right, so I'm going to erase it. Okay, so I'm going to redraw. And this is just x, and this is L over 2 minus x mg, and this distance from here to here is L minus x, and this is theta. So you can see this will be L minus x sine theta, this distance over here. All right. Okay, so there is a pivot over there. So there is a force here, which may be some arbitrary direction. So you can say this force has F. If this is the y direction, this is the x direction. So this is Fy and Fx from there. Over here, this is going to apply 90 degrees to that. So whatever the support is going to push against that at 90 degrees. So this is the F we want. And then you have an mg, a capital Mg of the bar at L over 2. And these are the forces on the bar. So A to B. So we have so this is 1, 2, 3, four forces on the bar. Okay, so how do we find this? That's the one we need to find, right? Which means you can do over there and then just get like too many equations. If we take this as a pivot, then you can see that this force is going to be counterclockwise torque, and this force will be the clockwise torque. And all I have to figure out is the lever arm. So from here to here is 90 degrees. So that distance is L minus X. So the F lever arm is just L minus X. How about mg? So from here, if you extend all the way here, this is the force of line of force for mg, and so we want that distance. Well, what that distance is going to be? This is L over 2, and this is theta, and this is theta. So this is going to be L over 2 sine theta. Because if you look into that triangle, we want this, and this is L over 2, and this is theta, and this is 90 degrees. So that's going to be L over 2 sine theta, and these two torques are supposed to balance. So F times L minus X is equal to mg L over 2 sine theta. So the F will be mg L over 2 sine theta over L minus X. Lots of problems like this, in a static equilibrium, they all follow very similar pattern. For instance, sometimes if you go back to this first problem, you might have problems like a person is standing here, or maybe this one again, someone walking, and at what point the person will go so that a certain amount of force applies on the bolt before the bolt breaks, So there will be a whole bunch of extension to these that you will come across. But I hope you got the strategy clear, because my message to you is to kind of focus on this equation and choosing the pivot, and you should be able to kind of address a whole bunch of static equilibrium problems. A lot of the students, because they are familiar with this forces, they go for that first, but that turns out to be not profitable direction for most problem solving. This will yield you much faster result in almost all the static equilibrium problems. But some problems, you can combine the two and to solve them. All right, that's all the strategies for static equilibrium problem solving. We are going to move on to the next chapter. That's on fluids, static fluids, pressure, how to find pressure in different situations, and surface tension. Later on, we're going to do viscosity and things like that. Okay, so see you in the next video. Bye.